We're going to talk about slope fields. When you have a first-order differential equation, that's an equation that involves a variable x, a function y, and this first derivative, dy dx. Write it in this standard form where you solve for dy dx. So you write dy dx as some function of x and y. Then draw a plane, and at each point in the plane, or many different points in the plane, draw a small line segment. At the point xy, draw the line segment whose slope is f of xy. When we do this, we'll see the following thing. If you have this example, dy dx equals minus x over y, for any solution y, which is a function of x, that satisfies this differential equation, at any point in the plane, say this is the point xy in the plane, a solution to this differential equation which goes through that point will have to have a tangent line which has the same slope as the slope of this little segment that you see. When we draw the graph of any solution to this differential equation going through that point, at every point along the solution curve, it should be tangent to the little segments in our slope field. This is a bad drawing, again, because I'm getting used to using this tablet. But wherever you start your solution curve, you'll need to have a solution which is everywhere tangent to the slope field. In this case, let's see how that works out. So, in this example, we have dy dx equals minus x over y, a typical first-order differential equation. We're going to learn methods for solving this differential equation, but I'll just run through a quick method here with all of you. We want to solve dy dx equals minus x over y. Just multiply both sides by y and write y dy dx equals minus x. Notice that the left side is precisely the derivative with respect to x of 1/2 y squared. Check that. How do you differentiate 1/2 y squared with respect to x? You get exactly y times dy dx. So we anti-differentiate to get 1/2 y squared, and we do the same on the right side. But remember, we have to add an arbitrary constant. You could actually add an arbitrary constant to both sides, but put them both on the right and call that c. This is an arbitrary constant. Then if we just solve for y, notice here we'll get two solutions. Y equals plus the square root of 2c minus x squared, and y equals minus the square root of 2c minus x squared. And this number 2c, since c is an arbitrary constant, we could call it d, a different arbitrary constant. So that can be any number here. Also notice that if this number d, or 2c, is negative, none of this will make any sense because you'll be taking the square root of a negative number. So d will have to be greater than 0. If it's 0, things also won't make any sense for any value of x except 0. So here we'll assume that d, which is 2c, is greater than 0. Now what does that mean? So pick a particular point for an initial condition. If we want to find a solution to that initial condition, say we want to solve the initial value problem, dy dx equals minus x over y, with, say, y of 0 equals 1/2. That means we're going to start at approximately this point. We're going to find a solution that goes through this point. In order to make y of 0 equal to 1/2, we would need to look here at our solution, y equals plus or minus square root of 2c minus x squared. We'll clearly need the positive part because we need, when x equals 0, y to be 1/2. And then we'll have y of 0 will be the square root of this number 2c, which I'll call d here, minus 0. So d will have to be This will have to equal, equals 1/2. So what does that tell you about d? If we square both sides, we get d equals 1/4. And then y is the square root of 1/4 minus minus x squared. Now, what does that solution curve look like? Well, you should be able to recognize this as the equation for the upper half of a circle of radius 1/2. And in fact, that's exactly what we get here. If I missed it here, a semicircle of radius 1/2, we get exactly that part. Given any point in the plane, we could solve for this constant d and choose the appropriate plus or minus, and we would get different solution curves. Let's look at a very different example. Here we have the example y prime equals 2 minus y, and I've shown you here the slope field. At any point xy in the plane, this slope of the little segment shown is exactly 2 minus the y coordinate. Notice that if you look at any particular vertical line here, let me get rid of that. That was not very good. I'm going to try to draw that again. If we notice all the slopes at any particular value of x, it's the same however you shift it to the right or left, because here your f of xy depends only on y and not on x. So if you pick any initial points, say here, we'll need a solution which is everywhere tangent to the slope field. Again, let me try to draw that a little better. You're going to get something that looks like this. Notice if you start right here where y equals 2, your solution will just be the constant y equals 2. And if you start a solution above the line where y equals 2, you'll get solutions that look like that. So we can tell an awful lot about what the solutions to this differential equation look like just from the slope field. Now we're going to see very shortly that it's easy to solve this differential equation, and I won't worry you right now about how you solve the differential equation. It won't be difficult. It's something we'll learn how to do very easily. But right now, I'll just claim all the solutions look like y equals a constant times e to the minus x plus 2. Already you can check. Even if you have no idea where I obtained this solution, you can check that y prime is minus c e to the minus x, and this is exactly 2 minus y. So you can see any solution of this form works, and if you give me any point in the plane, you can easily find the appropriate value c, such that this solution curve, the graph of this solution, goes through that point. What happens if you give me a point that starts out with y equals 2? Then you'll find the constant c will be 0, and you'll just get y equals 2, this constant function, as your solution. What happens if you start at the point 0, 0? What should c be? Well, then it's easy to tell that c has to be negative 2. So y equals minus 2 e to the minus x plus 2. And when you graph that, it really does look exactly like it's supposed to.